Anybody else want to decode? Okay, today around 8:30, I was looking at Beach Board and only 7 people submitted their homework. They were supposed to submit it before 8 o'clock. So still,
Professor?
yes,
Sorry, on the document you sent us, it says November 2nd.
I cannot hear you. What was it?
On the document that you sent us for the homework, it says it's due November 2nd, which is tomorrow. Yeah, on the document you sent us, it says November 2nd.
But you don't have a class tomorrow. I need to check that out because that could be a problem. The 2 classes are mixing the date. All right. Anyway, I'm gonna do the homework. The first homework, which is 1017, it's a little tricky. One, when you read the problem carefully, it's telling you this is an ideal simple ranking cycle. Ideal simple ranking cycle, the 0.3 is located on the saturated vapor line. So please pay attention when you're reading the problem. If it says ideal, that's where the 0.3 is. If it's just a simple ranking cycle, 0.3 would be in the superheated section. Now, the other trick is rather than giving you the pressure, they give you the temperature at 0.1 and 0.3. So there are 2 ways you can do it. You can go to the table based on these 2 temperatures on a saturated liquid table. You can find P1 and P2. As you can see, it's a very odd number and it's hard to go and find the values of H, which I did this year. However, rather than pressure, you can still use the 40 degrees Celsius, X is equal to 1, find H1 and V1. We can do that. And you can do the same thing at 0.3, rather than using this pressure that you find, you can use 250 degrees, but this time make sure H3 is H of G and S3 is S of G because 0.3 is located on the saturated vapor line. So if you know that, the value of H1 after interpolation and all of that becomes 167.53 kilojoule per kilogram. And this is 0.001008 meter cubic per kilogram. That would be the first edge. Going through the work of a pump, which is H2 minus H1, same as volume times delta P. Once you plug the number in, you find the value of H2 to be 171.54 kilojoule per kilogram. That's the second edge. Now again, this time you're still on the saturated liquid table. However, you're looking for H of G and S of G based on this pressure or based on 250 degrees Celsius. If you do that, the value of H3 becomes 2801 kilojoule per kilogram, and S3 is 6.721 kilojoule per kilogram degree Kelvin. So that's the third edge. 0.4 is in a mixture, so we have to go through this process. S of F would be 0.5724 And SFF of G is 6.0721. H of F, it's obviously same as H1, which is 167.53. And H of F of G is 24.06. So having all this value from this side, from the S value, since S4 is equal to S3, we have that value, we have S of F, we have S of F of G, and we plug it in, we can find the quality to be 0.7158. Then to this equation, H4 is H of F plus X4 times H of F of G. You find the value of H4 to be 1889.4 kilojoule per kilogram. So that's our final H value. I'm sorry, this is 0.8. Now that we have all the H value, the problem asks you to find the work of a turbine. Work of a turbine is equal to H3 minus H4. We have H3, we have H4. Once you plug it in, you find the work of a turbine to be 911.4 kilojoule per kilogram. To find the thermal efficiency, Q in is H3 minus H2, and the Q in value would be 2629.4 kilojoule per kilogram. The Q out would be H4 minus H1, and that value is 17222 kilojoule per kilogram. Finally, the thermal efficiency is 1 minus Q out divided by Q in, and this will give you 30.45% efficiency. That is the first problem. Again, the reason I picked this problem because I wanted you to pay attention of an ideal simple ranking cycle. That's number one. And also being able to use the temperature, finding the H values, or using the temperature, going finding the pressure, and going through a lot of interpolation in order to find H values. Any questions?
Can you step to the side, please, so I can see? Thank you.
Sure. While you're doing that, I'm going to do the TS diagram for the second problem. Are you done with this part?
Yes.
Okay. Now the second problem is reheat. And as you can see, based on the pressure of a reheat, which is 2 megapascal, we know for a fact that 0.4 isn't superheated, so we don't have to guess where that is. Now, again, this is pretty simple. The only difference is 0.5 and 0.3 have a different temperature. 0.3 has a 550 degrees Celsius, and 0.5 has 300 degrees Celsius. So that's something that we never do. But again, this is just for you to pay attention, because some problem, if you don't pay attention to it, you automatically assume they have the same temperature, and then later on you realize you made a big mistake. So please read the problem carefully. So this is pretty straightforward, reheat cycle. Again, this time, this is not the Q in, this is just the Q of the boiler. And then here, we're gonna have Q of the reheat. That goes right there, between 4 and 5. And we have 2, 3, and 4 is our first turbine, and 5 and 6 is our second turbine. We have only 1 point in the mixture area. So we start at state 1 at 50 kilopascal, and X1 being equal to 0, we'll find H1 and V1. H1 in this case is 340.54 kilojoule per kilogram, and V1 is 0.001 or 30 meter cubic per kilogram. At state 2, we have workable pump equal to H2 minus H1, which is same as V1 times P2 minus P1. Plugging everything in, paying attention, this is 17.5 megapascal. That means 17,500 kilopascal. You need to put there. Don't put 17.5, because that you're going to have a problem. In this case, our H2 value becomes 358.51 kilojoule per kilogram. At state 3, we have P3 equal to 17.5 megapascal, and T3 is 550 degrees Celsius. We are in a superheated region, so we go to superheated table. This time, we find H3 and S3. The value of H3 from the table is 23.6 kilojoule per kilogram. And the value of S3 is 6.4266 kilojoule per kilogram degree Kelvin. At state 4, we have P4 equal to 2 megapascal, that's our reheat pressure, and S4 is equal to S3. Once again, we are in a superheated table. From here, we find the value of H4 which is 2841.5 kilojoule per kilogram. At a state 5, we have P5 equal to 2 megapascal, and T5 is equal to 300 degrees Celsius. We're still in the superheated region. From there, we'll find H5 and S5. The value of H5 becomes 24.2 kilojoule per kilogram. And the value of S5 is 6.7684 kilojoule per kilogram degree Kelvin. At a state 6, we have P6 equal to 50 kilopascal, and S6 is equal to S5. Now, go to saturated liquid table, find the following values. The value of H of F is 1.0912, and H of F, S of F of G is 6.5019. H of F would be the same as H1, which is 340.54, and H of F of G is 2304.7. That's the TSI. Now, once again, from this side, we find X6 equal to S6 minus S of F divided by S of F of G. That will give us the quality of X6. We 0.8732, and H6, H of F plus, X6 times H of F of G. That will give us an H6 value of 2352.9 kilojoule per kilogram. Now, before I go further, I want you to just look at the answers that you find. That has to make your common sense. Otherwise, you are in a wrong. You're making a mistake, or you have made a mistake. H2 has to be bigger than H1, obviously, because it has a higher temperature and higher pressure. So as you can see, the difference is about 18 points. I said these pumps never get, never get more than 20 points. The work of a pump, the difference between H2 and H1. Now here we have an extremely high temperature, high pressure, and high temperature. So our value is 3,400 for the H3. And coming down to a state 4, my expectation that H4 has to be less than H3, and you see the result. Now going back to state 5, and going up again has to be bigger than that, but has to be less than this one. Why? Because this has a lower pressure and also lower temperature. As you can see, this is 3,400, this is only 3,000. Now, when I come down to a state, 6, obviously my 0.6 has to be much lower than state 5. And that's 33,000. This is about 2,300. So it's all make common sense going up and down, and you see the values dropping or going up. If you make any error in your calculation and you get the wrong numbers, then you can easily go back and fix it if you organize yourself. If you don't, and you write all over the paper, what happens if you make a mistake? You don't know where you made a mistake to go and fix it. And that was the problem on the first test. So please, get it organized, try to eliminate any mistakes. Now, in this case, we have Q in is equal to the Q of the boiler plus Q of the reheat. Now, Q of the boiler is H3 minus H2 plus Q of the reheat is H5 minus H4. This will give me the total Q in. So the total value of Q in is 3247.8 kilojoule per kilogram. Q out, it's only H6 minus H1, and that value would be 2012.4 kilojoule per kilogram. And finally, the thermal efficiency is 1 minus Q out divided by Q in, which give us about 38% efficiency. So that's the solution on the second problem. Have any questions? Now, while you're writing these things down, I'm going to Are you done with the left side?
Yes.
Okay. Now, this is a problem. If you don't read it carefully, you're going to have a major problem. Now, this problem, they did not give us the pressure between 0.4 and 5, the reheat pressure. They didn't give us that. However, what they did, they give us the quality at 0.6. So this is how we're going to solve this problem. We're going to go to state 1. We have a 10 kilopascal and x1 is equal to 0. This would be 191.81 kilojoule per kilogram, and this is 0.00101 meter cubic per kilogram. So that's our first H value. Again, work of a pump, H2 minus H1. Once we plug in the pressure, we find the value of H2. $206.95. So as you can see, the pumps on a reheat cycle are larger than the regular, Rankine cycle. The difference between these two, it's about 15 kilojoule per kilogram. So that's the second H2. Now we go to point 3, we have 15 and 500 superheated. The value of H3 becomes 3310.8 kilojoule per kilogram, and S3 is 6.3480. Now, I don't have any information on the pressure at point 4 and 5. So what I do, I leave this alone at this point. So I go to state 6. And at state 6, I have P6 equal to the 10 kilopascal, and X6 is given to be 0.95. So, and I know that S6 is also equal to S5. This is very important. Based on this, I can write S6 is equal to S of F plus X6 times S of F of G. Now here, based on this pressure and quality, I can find S of F, S of F of G, H of F, and H of F of G. Now the value of S of F $7.4996. Oops, sorry. 0.6492, and this is 7.4996. H of F is 191.81. And H of F of G is 2392.1. So now, to these two equations, I can find S of 6 and H6. So very quickly, the value of H6 becomes 2464.3 kilojoule per kilogram. And here, S of 6 value becomes 7.7739 kilojoule per kilogram dB Kelvin, that's S of 6, which we know S of 6 is equal to S5. So now I come back here. I don't have the pressure. So what I do, I use S of 5, which we found to be 7.7739. These are my 2 point of references. Now, in this case, I can find H5 and P5. So I have the temperature, I have the S value. We usually have temperature and pressure finding H5 and S5. Now we have S5 and T5, we can find H5 and P5. From that exercise, we can find the value of H5 to be 3479.3 kilojoule per kilogram. And this becomes 980 kilopascal, or approximately 1 megapascal. Now that I found the pressure, I go to state 4. I have 980 kilopascal, and S4 equal to S3, which is 6.3480. I can go to superheater table and very quickly find the value of H4, and that would be 26660 kilojoule per kilogram. So as you notice, we finished state 3. Since we didn't have the information in state 5, we left it alone, went to state 6. Based on the quality and the pressure, we found the S of F of G, H of F, and H of F of G. Through these 2 equations that we constantly use, this time we find S6 and H6. So that's the value of H6, and this would be the value of S6. We know for a fact that S6 in the same line, isotropic line, as S5. Now that I have S5, I come back here, based on the temperature and S value, I find H value and the pressure. Now that I have the pressure, I know that P4 is equal to P5. I go back to state 4 using that pressure, and S4 being equal to S3, I find the value of H4. So we work our way backwards. At the end of the day, once again, our curing this time, they give us a mass flow rate. So in this case, our Qing becomes 47,000 kilowatts, or 47 megawatts. Similarly, our Q out is H6 minus H1 times the mass of the steam. If we do the same thing, plug in mass, by the way, was 12 kilogram per second. So in this case, our Q out becomes 27,270 kilowatt. Now, This time we have Q out over Q in. And this becomes 42%. That's the thermal efficiency. Any questions?
I have a quick question.
Sure.
For state 4, when you went to the superheated table, since 980 kilopascals isn't in there, would you just have to interpolate to find H4 then?
Obviously, if you want an accurate answer, you need to interpret. The other way, if you remember, I wrote this one down. Approximately 1 megapascal. To make it easy for yourself, if you write 1 megapascal, you find the value a little bit different than this, but it's not that big of a deal.
Okay, so I missed that part right there. So yeah, thank you for clarifying.
Yeah, you can always, once you find its actual value, you can say, assuming P5 is equal to P4 and is equal to 1 megapascal. No harm done. Because 980 to 100, it's only 20 kilopascal, and it's really not that big of a deal. And your number, if you look at the table, it's not going to be that strange number that's very high or very low. It's going to be just a little tad difference.
All right, thank you.
Not a problem. Any other question? Now, the next problem is open feed water heater. Again, our open feed water heater 0.6 is in a mixture. The reason for it, because we have 400 kilopascal. We said anything above 600, your point is in a superheated. If it's less than that, it's in a mixture. Generally, in the industry, we don't do that. We don't use that kind of a pressure. We increase the pressure to make sure that 0.6 in a superheated, so we get a better deal. And this is 20 kilopascal. And this one is 6 megapascal. Temperature at 0.5 is 450 degrees Celsius. Now, as you know, Y is going between 0.6 and 3. And here we have 1 minus Y, going from 6 to 7. Of course, that 1 minus Y come all the way to 0.1 and to 0.2. Then they join 0.3, add y to it, becomes 1 unit all the way. So now, once again, we saw that the state 1, P1 is 20 kilopascal, and X1 is 0. So I find H1 and V1. The value of H1 is 251.42 kilojoules per kilogram. The value of V1 is 0.00107, I'm sorry, 117 meter cubic per kilogram. And in state 2, we have workable pump 1, which is H2 minus H1, which is the same as V1 times P2 minus P1. From here, once we plug the number in, we find the value of H2 to be 251.81 kilojoule per kilogram. Once again, if you compare these two, this is about 0.39. That's a very, very small pump. That your first pump is very small. Second pump is much larger than the first pump. So at state 3, we have P3 equal to 400 kilopascal, and X3 is equal to 0. So now we find H3 and V3. From the table, we can find the value of H3 to be 604.66 kilojoule per kilogram, and V3 is 0.001084 meter cubic per kilogram. So that's our third H value. At state 4, we're going to repeat that step. This time, workable pump 2 is equal to H4 minus H3, which is same as V3 times P4 minus P3. Once we plug everything in, we find the value of H4 to be 610.73 kilojoule per kilogram. And if you compare H4 and H3, the difference between them, workable pump, this is about 6.08. So not bad. This pump has to be bigger than the first one. Now we go to state 5. At state 5, we have P5 equal to 6 megapascal, and T5 is equal to 450 degrees Celsius. We are in superheated table, so we find H5 and S5. Keep in mind that S5 is equal to S6 is equal to S7. They're all in the same isentropic line. So the value of H5 at this point would be 3302.9 kilojoule per kilogram, and S5 would be 6.7219 kilojoule per kilogram degree Kelvin. At stage 6, we have P6 equal to 400 kilopascal, and the 6 being equal to S5. Now this time, since we are in a mixture area, we're going to find S of F, S of F of G, and then H of F of G. The value of S of F is 1.7765, and S of F of G is 5.191. Oops. 5.1191. H of F at 0.6 would be the same as H3. H3 is 610.70. 610.73. And H of F of G would be 2133.4. Again, from this side, we find X4 to be S4 minus S of F divided by S of F of G. So we get upside, S6. X6 becomes 0.9661. And as you notice, my 0.6 is pretty close to saturated vapor line. That's why the quality is 0.9661. So H6, which is H of F plus X6 times H of F of G. From there, we find the value of H6 to be 2665.7 kilojoule per kilogram. And at state 7, we have P7 equal to 20 kilopascal, and S7 being equal to S5. One more time, S of F, S of F of G, H of F, H of F of G. The SF value would be 0.8320, and S of F of G is 7.0752. H of F is same as H1, which is 251.42. And H of F of G is 2375.5. Now, in this case, we're going to use the same equation to find X7. So if you plug everything in, we find the value of X7 to be 0.8325. Now, look at X7 and look at X6. 0.7 is further away from saturated vapor line. So their quality should be much less than quality at 0.6. And you see that. If you ever have this quality bigger than quality at 0.6, you definitely done something wrong in your calculation, because this line is coming down straight forward, not zigzagging. So that's how you can check your answer at all time. Now, putting X7 in the same equation that we have here, we will find the value of H7 to be 2214 kilojoule per kilogram. That's our final H value. Now, before we go further, we need to write summation of all energy going into that feed water has to be summation of all energy going out of that feed water. Now, what goes in is M6, H6. At 0.6, that's where we take that into the feed water. Plus M2H2 goes to that feed water heater. What comes out is M3H3. I call this one a Y. And if I look at 1 minus Y come all the way to 0.2, that would be 1 minus Y times H2. At 0.3, 1 minus Y and Y get together becomes 1 unit. So that's 1 unit times H3. I have all the H values. I have one equation, one unknown. From there, I can find the value of Y to be 0.1462 or 14.5% that I'm extracting from the turbine to put it in a feed water heater. Now that I have that, my Q in would be H5 minus H4, and that gives me a Q in value of 2692.2 kilojoule per kilogram. The Q out has a fraction in front of it. 1 minus Y times H7 minus H1. And that will give me a value of 1675.7 kilojoule per kilogram. So I have my Q in, I have my Q out. Net work would be Q in minus Q out. And that gives us a value of 1.622. 0.5 kilojoule per kilogram. This is our network. Now to find the thermal efficiency, since they asked me to find the network, so I put the network divided by Q in. And this will give me 37.8% efficiency. We will have getting probably 3 or 4 points more efficiency if 0.6 was in a superheated region. Any questions?
Yes, Professor.
Go ahead.
You said that the H of F for state 6 is the same as H of 3, right?
No, I didn't say H6 is that. I said H of F at 0.6 is the same.
Yeah, the top one. The top one.
Wait a minute. Where are we?
Yeah.
Say 6. So this.
Yeah, because that's H of
I put H4 value, right?
yeah.
That should be 604.6. Thanks.
Yeah, no problem.
I accidentally look at the wrong number.
I have a question.
Sure.
Is M.3 usually 1? Or is it always 1?
What was the question?
M.3, is it always 1? Like the
M.3. You need to look at the actual diagram. We don't know what the value of M.3 is. We consider that as a 1 unit. If it's not 1 unit, see, this is 1 unit, 1 unit, 1 unit, 1 unit. When it comes here, we take Y in this direction, 1 minus Y, this is 1, and I take y and go in this direction, this has to be 1 minus y. So 1 minus y here, 1 minus y here, 1 minus y between 1 and 2. And when it gets to 3, I add y to it, becomes 1 unit. 1 unit, 1 unit, 1 unit, split again. So we're not looking at the value of m dot 3 to be 1. The value of m could be anything. They can tell us that m is 200 kilogram per second. But we consider it as a 1 unit, regardless of its weight. It's a 1 unit. And we split it to y and 1 minus y. So it's not that the value of m is equal to 1. We call this as a 1 unit because that was the assumption we made, that if this is 1 unit, we take a y going this direction, what is the balance of it? 1 minus y. Now, if the problem at the beginning would have told us that you take 14% this direction, and therefore 86% would go that direction. And if the value of M3 was, 200, we will take 14% of it go this direction, 86% of it, 200, going that direction. We have the value. Since we don't have the value of m, we consider it as 1 unit. Go back, take a look at your notes on what we did in open feed water heater.
Okay, yeah, I remember now. Thank you.
Not a problem. It's not that it's a value is 1. We assume that's a 1 unit. It's a different considering it 1 unit, that considering it 1 as a value of m. Now, the next one is a little crazy cogeneration. I'm going to draw the diagram and I tell you that why this kind of a cogent is awkward and will never work. Now, if you look at the diagram, they have the boiler here. That's the process heat. Then this line continues going to open feed water heater. And then going to condenser. Now, this is our point 1, point 2. Now, this has not been identified. This is point 7. This one, they call it point 9. Of course, coming out of feed water heater is 0.3. This one is 0.4. This is 0.5. 6. And this is 8. Now, this type of a cogeneration, the only way this type will work if there is a valve here. Now, if they want to have a cogen, this goes this direction, the feed water heater becomes at, right here at this point. And that's the way we did it. Now, if they don't want to use the process, this becomes a regular feed water heater. This 0.7 becomes here, and the whole thing is going to go away. So you're shutting one side down, the feed water side, you have a cogen. You're shutting the cogen down, you have a feed water heater. Why you want to do that, it's beyond me. It's a waste of time and money to do something like that. Now, the TS diagram for that, now keep in mind, 0.3 and 4 and 9 coming to one point. How you connecting to a regular pipe, 0.3 coming out, 0.9 coming, joining that, and then 0.4 goes out again. You have to have a mixture to mix this because this has a different temperature than that, than this one. But on the TS diagram, they're making an assumption now, this is the TS diagram. In a cogen, we never put the 0.7 in a mixture because it doesn't work. Having this 0.3, 4, and 9 merging at one point, assuming they all three of them having the same temperature, that's impossible. So that's why nothing's in this concept going to work. And they don't identify this 0.7 that goes to cogen, how much of it goes there and how much of it comes to the feed water heater. It is obvious that 0.7 goes either to cogen or going to the feed water heater. So it's not working at the same time. So again, if you want to do this problem, let's see. That is another one. The TS diagram is wrong. 0.7 has to be in because this is 1.6 megapascal. There is no way that 0.7 would be in a mixture area. And then at the top, we have 9 megapascal. Temperature at 0.6 is 400 degrees Celsius. So, They didn't give us a mass flow rate. They are asking us to find the mass flow rate. That's another crazy thing. If you really look at this problem, they didn't solve for the Q process. So in reality, this is another open feed water heater. All these are all gone because they're not asking us to find the Q process. They're not asking us to find the utilization factor of a cogen. So this is just a regular feed water heater. This is exactly what we saw last time. Is it okay if I erase this?
Wait, hold on, Professor.
Right?
I said, hold on. I'm gonna take a picture.
This should be on your text when you look at the problem. They have this diagram. But that's okay.
I'm not sure if I did it right, but when I got to state 7, I found it to be a mixture.
0.7 is going to be in the mixture.
Yeah, when I found the entropy of 0.6, it was, and then at 0.7 at 1.6 megapascals, it looked like the entropy was lower than the superheated table, so I put it in a mixture.
But that, well, I don't know, because I never seen this kind of a pressure, 1.6, almost 3 times the one that I told you has to be superheater, and still being in a mixture area. So that's fine if that's how they did it, we'll do it that way. 0.7 in a mixture. Because it doesn't make any sense. With that kind of a pressure, there is no way that 0.7 be in that situation. Anyway. Now, again, as a state 1, we have P1 equal to 10 kilopascal. X1 is 0. I will have H1 191.81 and V1 is 0.00101. So that's 1H. At a state 2, I have work over pump 1, H2 minus H1, or V1 pump times P2 minus P1. This will give me the value H2 be 193.41 kilojoule per kilogram. State 3, I have P3 1.6 megapascal, X3 is equal to 0. And this will give me a value of H3 to be 858.44 kilojoule per kilogram, which is equal to H4, which is equal to H9. And V3 becomes 0.001159 meter cubic per kilogram. And state 5, I have H5 minus H3, which is equal to V3 times P5 minus P3. So H5, that's a workable pump 2. The value of H5 becomes 867.02 kilojoule per kilogram. At state 6, I have P6 equal to 9 megapascal and T6 equal to 400 degrees Celsius. Superheated table. I found, H6 and S6. So the value of H6 is 3118.9 kilojoule per kilogram, and S6 is 6.2876 kilojoule per kilogram degree Kelvin. So that's, we have only 2 more points to calculate, state 7 and state 8. God, we're running out of time. If you go to the mixture, find S of F, S of F of G, H of F, H of F of G, you find the value of X7 to be 0.9675, and H7 therefore would be 2730 kilojoule per kilogram. You do the same thing for 0.8, and you find the value of X8 to be 0.7518. And H8 in this case would be 1990.2. Now, the value of Y, the percentage, was given to be 35%. That's it. Basically, when we extract 35% going that direction, 65% going this direction. So in this case, we have W of a turbine total would be the first turbine, which is H6 minus H7, plus 1 minus Y times H7 minus H8. We have this as a 35.035. So we can find that W turbine to be 869.7 kilojoule per kilogram. Work of a pump total. The first pump has 1 minus Y because that comes in as a 1 minus Y. 1 minus Y times H2 minus H1 plus H5 minus H3. So total work of the pump becomes 9.62 kilojoule per kilogram. Therefore, our net work is equal to W turbine minus W pump. That will give us a net work value of 860.1 kilojoule per kilogram. The mass of the steam is big W dot net divided by small W net. This is what we found here. The total is 25 megawatt, which is 25,000 kilojoule per second, divided by 860.1 kilojoule per kilogram. This kilojoule cancel each other, so our mass would be kilogram per second. So this becomes 2019.1 kilogram per second. That is a very strange cogent plan, because we don't know why we talk about, this is an open feed water heater telling us the value of Y, so we don't have to calculate it. That's it. There is nothing special about this to call it cogent, because we didn't find out what is the Q process and what is the effectiveness or utilization factor of this cogent. As you notice, they didn't ask for thermal efficiency, because once you call it a cogent project, you cannot, ask for thermal efficiency. You have to ask for utilization factor, which they didn't. So this was a very strange exercise. I make sure that I never give that assignment anymore, because that was very, very strange. Any questions?
Professor, a
Yes.
quick question. For the work of the turbine total, is there supposed to be a Y before the H6 minus H7?
We discussed this several times. There's no Y coming here. 0.6, this is 1 unit, this is a part. At this point, we split 0.7, that's where the Y goes this direction. There is no Y here.
Okay.
Do you remember we discussed this?
Yeah, we did. I guess I get mixed up between the diagrams again, but thank you.
No. Keep in mind, the exit is 0.7. The entrance is 0.6. Between 6 and 7, there's no Y. When it exits, 35% go this direction, and the balance of it goes that direction. Any other questions?
Professor, can you step aside? I can't see the entire board. Is it okay?
Not a problem.
What's the value for the mass? The light reflection.
Oh, not a problem, not a problem. It's 29.1 kilogram per second.
Thank you.
Because we ran out of time, I was writing too fast. I don't blame you if you can read my handwriting. But I'm glad you're asking so I can clear that up. If you have any other part that you don't see it, please let me know.
So do we have until tomorrow morning to turn in our homework since it's set down by
Yeah,
doc?
if there was an error, that's fine.
Okay, thank you.
Now, for those of you who have any question, you want to stick around for my office hour, please stick around. If not, we'll see you Wednesday. We're going to continue chapter 11.
All right, thanks, Professor.
No problem, my pleasure.
Thank you.